Now in this lecture we'll answer two questions. In the first question we'll find out the area of the circle, and in the second question we'll find out the area of trapezoid ABCD. So we'll start with the first question. In the drawing we have a circle, and we have also the right triangle ACP. The right triangle ACP, that's the circle 2 points A and this point. We know that side CP of this right triangle ACP equals to 4 units in itself. This is angle ACP, that is the right angle, and last side VC equals to 1 unit in itself. Again, our mission is to find out the area of this circle. So first of all, we'll implement here rule 2. Well, if we focus on the common standpoint point P, from the common standpoint point P we have two tangents to this circle, PA and PB. And according to rule 2 they are equal to each other. That is to say PA equals to PB. So write it down. According to rule 2, PA equals to PB. But PB, according to what is given as the question, PB in total equals to 1 plus 4, that is 5. We can write here that PB equals to 5. And from this equation, PA equals to PB equals to 5. We derive that PA is also equals to 5 units in itself. PA equals to 5. PA equals to 5. In the next step, I'll copy the right triangle ACP in the new page, and we replace the Pythagoras theorem on this right triangle ACP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the version for Pythagoras theorem. So actually, this is the right triangle ACP that I quote from the original drawing. According to the Pythagoras theorem, in this right triangle ACP, AP square equals to AC square plus CP square. So write it down. AP square, that is the square of the hypotenuse, equals to AC square plus CP square. AP is 5, therefore AP square is 5 squared, that is 25. And it is equals to AC square. AC is the missing side, so we leave it as it is, so it is AC square plus CP square. CP is 4, therefore CP square is 4 squared, that is 16. So in total we found out that 25 equals to AC squared plus 16. Here subtract 16 from this equation. And finally we get that AC squared equals to 25 minus 16 is 9. So AC squared equals to 9. Here we take a root out of this equation and finally we get that AC equals to the square root of 9, that is 3. So we found out that the left of the missing side AB is 3 units. So I write down here that AC equals to 3 units in its length. In the next step, we'll define the center of this circle. This point is point O. And we'll also define the radius of this circle as X. So in the next step, we'll join points O and B together by a straight line. Point O is the center of the circle, and point B is the point of the circle itself. So this is exactly the definition of a radius. Therefore, OB is the radius of the circle, that is equals to X according to our definition. So here we can implement rule 1. Because we have the radius OB that is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees. PB is a tangent to this circle according to what is given as the equation. So PB is a tangent, it is absolutely a straight line. So if we focus on the upper side of the straight line PB, it's point C. Here the sum of the angles must be equal to 180 degrees according to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of PB at point C? We have this angle that is right angle plus this missing angle. In total they must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we will do a construction, that is to say, from this point O, that is the center of the circle, we will do perpendicular on AC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AC, this point is point F. By doing this construction, we create quadrilateral OFCB. Inside quadrilateral OFCB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral OFCB we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be a right angle if not a square. So we relate to quadrilateral OFCB is a right angle because it has 4 right angles. So I have in mind quadrilateral OFBC is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle DFCB, side BC must be equal to the opposite side OF. But BC is 1, therefore OF must be also equal to 1 unit in its length. Likewise, according to the same rule, in the same rectangle OFBC, side OB must be equal to the opposite side FC, but OB is x, therefore FC must be also equal to x units in its length. What is the length of line segment AF? For the drawing, it is very easy to see that AF equals to AC minus FC. Again, AF equals to AC minus FC. So write it down. AF equals to AC minus FC. So AF equals to AC is 3 minus FC is x. So in total, we actually found out that AF equals to 3 minus x units in its length. In the next step, we will join points O and A together by straight line. What is the definition of line segment OF? Line segment OA starts from point O, that is the center of the circle, and ends at point A, that is the point on the circle itself. So this is exactly the definition of a radius. Therefore, OA is the radius of the circle that is equal to x according to our definition. So in the next step, I'll copy the right triangle OEF in a new page, and we'll implement the Pythagoras theorem of this right triangle OAF. Here by PT is the version from Pythagoras theorem. So clearly this is the right triangle OEF that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle OEF, AO square equals to AF square plus FO square. AO square, that is the square of the hypotenuse, equals to AF square plus OF square. OA equals to x, AF equals to 3 minus x, and OF equals to 1. AO is x, therefore AO square is x square, and it is equals to AF square. AF is 3 minus x, therefore AF square is 3 minus x square, plus OF square. OF is 1, therefore OF square is 1 square, that is 1. So in total, we found out that x square equals to 3 minus x square plus 1. Here we'll open the brackets on this side of the equation, and finally we get that x square equals to 3 minus x square equals to 3 squared, that is 9, plus x square, plus 2 times 3 times x, that is minus 6x, plus 1. So here we have x square on both sides of this equation, so x square will get cancelled. Once I cancel x square, on this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have 9 plus 1, that is 10, minus 6x. Here we add 6x to this equation, and we get that 6x equals to 10. So here we'll divide this equation by 2, and finally you get that 6x over 2 is 3x equals to 10 over 2 is 5. So 3x equals to 5. Here we'll divide this equation by 3. And finally you get that x equals to 5 over 3 units in its length. That is to say, we actually found out that the radius x of this circle is equals to 3 over 3 units in its length. Our mission is to find out the area of this circle. The area of any circle equals to pi times the radius of the circle squared. So write it down. The area of any circle equals to pi times the radius of the circle squared. So it is pi, and the radius of our circle is x. Therefore the radius squared is x squared. So in total we found out that the area of our circle equals to pi x squared. And what we just right now found out that x equals to 5 over 3. Therefore x will be equal to 5 over 3 squared. So it is pi times 5 over 3 squared. So it is equals to pi times 5 over 3 squared. 5 over 3 squared equals to 5 squared, that is 25, over 3 squared, that is 9. So in total we found out that the area of this circle equals to either 25 pi over 9 square units, so in terms of numbers, the area of this circle equals to 8.727 square units. So writing down, is equals to 8.727 square units. So we'll finish with the first question. In the next step, I'll present you the second question and we'll solve it. Our mission in the second question is to find out the area of this trapezoid ABCD. So we know that side AD equals to 17 units in its length, side AB equals to 16 units in its length, side BC equals to 25 units in its length, and finally side DC equals to 44 units in its length. Actually, we know that the area of any trapezoid equals to the sum of its two parallel bases times the height over 2. So in our trapezoid ABCD, the two parallel bases are AB and DC. So the sum of the two parallel bases is AB plus DC times the height, that is h. The height must create 90 degrees with the other two bases, divided by 2. So write it down. The area of trapezoid ABCD is equals to the sum of the two parallel bases that are AB plus DC times the height. The height must create 90 degrees with the two bases. So we define the height as h divided by 2. Fill again, in total the area of trapezoid ABCD will be equal to the sum of its two parallel bases, that is actually AB plus DC, times the height, that is h times 2. Again, the height must create 90 degrees with the two bases AB and DC. Okay, so in the first step we will do a construction. That is to say, from this point A, we will do perpendicular, on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in DC. This point is point E. We define the length of side DE as X. Likewise, we define the length of AE as H. Actually, AE is the height to the base, the height of trapezoid ABCD, because it creates 90 degrees with the base TC. So AE equals to H according to our definition. The next step, I'll copy the right triangle ADE in the new page, and we'll implement the Pythagoras theorem with this right triangle ADE. Here by PT is evolution for Pythagoras theorem. So actually, this is the right triangle ADE that is called to original drawing. The hypotenuse AD equals to 17 units in its length according to what is given as the question. AE equals to H according to our definition, and DE equals to X according to our definition also. So according to the Pythagoras theorem, in this right triangle ADE, AD squared, that is the square of the hypotenuse, equals to AE squared plus DE squared. So I write it down. AD squared, that is the square of the hypotenuse, equals to AE squared plus DE squared. The hypotenuse AD equals to 17 units in its length, therefore AD squared is 17 squared, that is 289. And it is equals to AE squared. AE is H, therefore E squared is H squared plus DE squared. DE is X, therefore DE squared is X squared. So in total we shall find out that according to equation 1, H squared plus X squared equals to 289. In the next step, we'll do another construction, that is to say, from this point, point B, we'll draw perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the construction. We define the touching point of the perpendicular from point B in DC. This point is point F. We We know that AB is parallel to DC. Again, AB is parallel to DC. So those two angles are located inside the parallel lines AB and DC, and therefore they are defined as in interior angles. And those two angles, they are located both in the left side of the straight line BF, and therefore they are defined as one-sided angles. So in total, those two angles, they are defined as one-sided interior angles. And according to rule 16, the sum of two one-sided interior angles is equal to 180 degrees. Okay, again, according to rule 16, the sum of one-sided interior angles is equal to 180 degrees. Those two angles are defined as one-sided interior angles, therefore the sum of them is equal to 180 degrees. So angle 4 plus angle 5 equals to 180 degrees. Those two angles are also defined as one-sided interior angles, and therefore the sum of them is equal to 180 degrees. That is to say, angle 3 plus angle 6 equals to 180 degrees. According to this rule, rule 16. So we can actually implement rule 16 in our drawing. Why? Because in our drawing we have those two interior angles that are also one-sided angles, and according to rule 16, the sum of those two angles is equal to 180 degrees. This angle equals to 90 degrees plus the size of this missing angle. In total, they must be equal to 180 degrees according to rule 16. So write it down. We actually found out that this is a right angle. This is to say it is equal to 90 degrees in size, plus the missing angle, that is actually angle ABF. In total, the sum of those two angles must be equal to 180 degrees according to rule 16. Okay, again, I found out that the sum of the two interior one-sided angles, that is to say 90 degrees plus the size of angle ABF, they are both one-sided interior angles. The sum of them must be equal to 180 degrees according to rule 16. Here we subtract 90 degrees from this equation. Finally, we get that the missing angle ABF is equal to 180 degrees minus 90 degrees is 90 degrees. So the missing angle ABF equals to 90 degrees in its size. This is the missing angle ABF, that is equal to 90 degrees. Likewise, we will implement rule 16 on those two angles. Again, those two angles, they are located between the parallel lines AB and DC, and therefore they are defined as interior angles. And those two angles, they are both located in the left side of the straight line AE, and therefore they are defined as one-sided angles. And so in total, those two angles are defined as one-sided interior angles, and the sum of those two angles must be equal to 180 degrees according to rule 16. So this angle equals to 90 degrees in its size, plus this missing angle, that is actually angle BAE. In total, the sum of those two angles must be equal to 180 degrees according to rule 16. Here again, the sum of those two angles is actually 90 degrees plus the missing angle BAE. The sum of those two angles must be equal to 180 degrees according to rule 16. If we subtract 90 degrees from this equation, and finally we get that the missing angle BAF is equals to 180 degrees minus 90 degrees is equals to 90 degrees. So we found out that the missing angle BAE, this angle must be equal to 90 degrees in its size. So we found out that in size quadrangle ABFE we have 4 right angles. And according to rule 5, any quadrangle that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrangle ABFE is a rectangle because it has 4 right angles. So write it down. This quadrangle ABEF is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABFE, side AB must be equal to the opposite side FE. But AB is 16, therefore FE must be also equal to 16 units in its length. Likewise, according to the sum rule, in the sum rectangle ABFE, side AE must be equal to the opposite side BF. But AE is 8, therefore BF must be also equal to 8 units in its length. What is the length of the missing line segment FC? For the moment, it is very easy to see that FC in total equals to DC minus DE minus EF. Again, FC in total equals to DC minus DE minus DF minus EF. Again, FC in total equals to DC minus DE minus EF. So right now, FC equals to DC minus DE minus EF. So in total, FC equals to DC, that is 44, minus DE, that is X, minus FE, that is 16. So in total, FC equals to 44 minus X minus 16. So FC equals to 44 minus 16 is 28 minus X. So in total, we found out that FC equals to 28 minus X units in its length. Write it down, FC equals to 28 minus X units in its length. So in the next step, I'll copy the right triangle BFC in the new page, and we will implement the Pythagoras theorem with this right triangle BFC. Here by PT is the version for Pythagoras theorem. So actually, this is the right triangle BFC, that is according to the original drawing, according to the Pythagoras theorem. This right triangle BFC, BC squared, that is the square of the hypotenuse, equals to BF squared plus FC squared. So write it down. This will be equation 2, according to equation 2. And the Pythagoras theorem, BC squared, that is the square of the hypotenuse, equals to BF squared plus fc squared. BC is 25, therefore BC squared is 25 squared, that is 625, and it is equal to BF squared. BF is h, therefore BF squared is h squared, plus fc squared. fc 28 on x, therefore fc squared is 28 on x squared. So in total, if we found out that according to equation 2, 625 equals to h squared, 625 equals to h squared plus 28 on x squared. Here we'll open the bracket on this side of the equation and finally get that according to equation 2, $625 equals to h squared, and we have here 28 minus x squared. 28 minus x squared equals to 28 squared, that is 784, plus h squared minus 2 times 28 times x is minus 56x. So repeat again, according to equation 2, I found out that $625 equals to h squared plus 784 plus x squared plus 56x. So here we subtract 625 from this equation. After we subtract 625, in this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have h squared plus x squared minus 56x, and 784 minus 625 equals to 159. So in total we found out that 0 equals to h squared plus x squared minus 56x plus 159. Actually, we found out that according to equation 1, h squared plus x squared equals to 289. Therefore, we can substitute x squared plus x squared here in this equation 2 by 289. We'll do it now and we will get that according to equation 2. Zero equals to h squared plus x squared is 289 according to equation 1, minus 56x plus 159. Here we'll add 56x to the equation and we get that according to equation 2, 56x equals to 289 plus 159 equals to 448. So in total, we found out that 56x equals to 488. Here we divide this equation by 56. And finally we get that x equals to 448 over 56. So x equals to 8 units in its length. But in equation 1, we only found out that according to equation 1, h squared plus x squared equals to 289. We just right now found out that x equals to 8, therefore x squared must be equal to 8 squared, that is 64. Therefore we can substitute x squared in this equation 1 by 64. We'll do it now, we get that according to equation 1, h squared plus x squared is 64 equals to 259. So here we subtract 64 from the equation, and we get that h squared equals to 289 minus 64 equals to 225. So in total according to equation 1, we have found out that h squared equals to 225. Here we'll take the root out of this equation and finally get that according to equation 1, h equals to the square root of 225, that is 15. So if you found out that the height edge of this trapezoid ABCD is equal to 15 units in its length, our mission is to find out the area of trapezoid ABCD. So what is the area of trapezoid ABCD? The area of trapezoid ABCD equals to the sum of its two bases, the sum of its two parallel bases, that is to say AB plus DC times the height, that is h, divided by 2. So let's write it down. The area that we're looking for, that is the area of trapezoid ABCD, equals to the sum of its two parallel bases, that is actually AB plus DC times the height, that is h, over 2. So the area of trapezoid ABCD in total equals to AB, that is 16, plus DC, that is 44, times h, that is 15, divided by 2. 16 plus 44 is 60, over 2 times 15. Again, 60 over 2 times 15. 60 over 2 is 30 times 15. So in total, we found out that the area of trapezoid ABCD equals to 30 times 15, that is 450. So the area of trapezoid ABCD is equals to 450 square units. So in the next step, repeat again, the area of this trapezoid ABCD equals to 450 square units. In the next step, I will summarize the lecture. We'll start with the first question, of course. Our mission in the first question is to find out the area of this circle. So in the drawing we have a circle, and from this common example point P, we have two tangents to this circle, tangent PA and tangent PB. In addition, we also have the right angle ACP that cuts the circle at 2 points, A and this point. We know that side CP of the right angle ACP equals to 4 units in itself. This is angle ACP, that is the right angle. This right angle BC equals to 1 unit in its length. Again, our mission is to find out the area of this circle. Okay, so first of all, we implemented rule 2. in our drawing. According to rule 2, if we focus on this current some point B, we have two tangents to the circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say PA equals to PB. So again, according to rule 2, PA equals to PB. But PB, according to what is given as the question, PB equals to 4 plus 1, that is 5. So PB equals to 5, we can write here that PB equals to 5, and from this equation PA equals to PB equals to 5, we'll write that PA must also equals to 5 units in its length. Here PA equals to 5 units in its length. In the next step, I copied the right triangle ACP in a new page and implemented the Pythagoras theorem on this right triangle, triangle ACP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This is the right triangle ACP that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle ACP, AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. AP is 5, therefore AP squared is 5 squared, that is 25, and it is equal to AC squared. AC is the missing side, so we'll leave it as it is, so it is AC squared plus CP squared. CP is 4, therefore CP squared is 4 squared, that is 16. So in total we shall find out that 25 equals to AC squared plus 16. Here we subtract 16 from this equation, and finally found out that AC squared equals to 25 minus 16 is 9. So AC squared equals to 9. AC squared equals to 9. Here we took out all of the equation and finally found out that the missing side AC equals to the square root of 9, that is 3. AC equals to 3, so we can write here that AC equals to 3 in its length. In the next step, we define the center of this circle, this point as point O. And we also define the radius of this circle as x. In the next step, we join points O and B together by a straight line. Point O is the center of the circle, point B is the point of the circle itself, therefore OB is the radius of the circle, that is equals to x according to our definition. So OB equals to x. Here we can implement rule 1. Why? Because we have the radius OB that is known to point B, that is the point of tendency of tangent PB with this circle. And whenever you have a radius that is known to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. PB is a tangent to the circle, so PB is a tangent, it is absolutely a straight line. So if you focus on the upper side of the straight line PB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. In this case, it means that the sum of the angles on the upper side of the straight line PB must be equal to 180 degrees. Or the sum of the angles on the upper side of the straight line PB at point C must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of PB at point C? We have this angle that is a right angle plus this missing angle. In total, they must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we did a construction. This is to say, from this the center of the circle, that is point O, we draw perpendicular on AC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AC. This point is point F. By doing this construction, we created quadrilateral OFCB. Inside quadrilateral OFCB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in size. So inside quadrilateral OFCB, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be intersect angle, front and square. So we relate to quadrilateral OFCB as right angle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle OFCB, side OF must be equal to the opposite side CB. But CB is 1, therefore FC must be also equal to 1. Likewise, according to the sum rule, in the sum material OFCB, side OB must be equal to the opposite side FC, but OB is X, therefore OFC must be also equal to X. What is the length of the missing line 7AF? From the drawing, it is very easy to see that AF equals to AC minus FC. Again, AF equals to AC minus FC. So AF equals to AC, that is 3, minus FC, that is X. So in total, AF equals to 3 minus X units in its length. In the next step, we join points O and A together by straight line. OA is the radius of this circle that equals to X. In the next step, I copy the right triangle AOF in the new page and we implemented the Pythagoras theorem of this right triangle, triangle AOF. Okay. This is the right triangle AOF, the right green triangle AOF, that I got from the original drawing. This right triangle AOF, AO squared, that is the square of the hypotenuse, equals to AF squared plus OF squared. AO is X, therefore AO squared is X squared, and it is equals to AF squared. AF is 3 minus X, therefore AF squared is 3 minus X squared, plus OF squared. OF is 1, therefore OF squared is 1 squared, that is 1. So in total, we found out that X squared equals to 3 minus X squared plus 1. Here we open the brackets of this expression and found out that X squared equals to 3 minus X squared is 3 squared, that is 9, plus X squared minus 2 times 3 times X, that is minus 6X plus 1. So here we have X squared on both sides of the equation, so X squared will get cancelled. After we cancel the X squared, this side of the equation we have nothing, that is to say 0. On the other side of the equation we have 9 plus 1, that is 10, minus 6x. So in total, we have found out that 0 equals to 10 minus 6x. Here we added 6x to this equation, and finally found out that 6x equals to 10. Here we divided this equation by 2, and finally found out that 6x over 2 is 3x, and 10 over 2 is 5. So in total, we found out that 3x equals to 5. Here we divided this equation by 3 and finally found out that x equals to 5 over 3 units in its length. That is to say, the radius of this circle x is equals to 5 over 3 units in its length. Our mission is to find out the area of this circle. Actually, the area of any circle equals to pi times the radius of the circle, or 2 pi times the radius of the circle square. Again, the area of any circle equals to pi times the radius of the circle squared. Therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is x. Therefore, the radius squared is x squared. So in total, the area of this circle must be equal to pi x squared. Again, the area that we're looking for must be equal to pi x squared. We just right now found out that x equals to 5 over 3, or 5 thirds. If x equals to 5 over 3, it means that x squared equals to 5 over 3 squared. So in total, the area of the circle that we are looking for is pi times 5 over 3 squared. So it is pi and 5 over 3 squared equals to 5 squared, that is 25, over 3 squared, that is 9. So in total, we found out that the area of this circle equals to either 25 pi over 9 square units, so in terms of numbers, the area of this circle is equals to 8.727 square units. Okay, so we finished with the first question. In the next step, I actually presented to you the second question, and we solve the second question. Our mission in this second question is to find out the area of trapezoid ABCD. It is given us in the question that AB equals to 16, BC equals to 25, AD equals to 17, and side DC of this trapezoid ABCD equals to 44 units in its length. Again, our mission is to find out the area of this trapezoid ABCD. Actually, we know that the area of any trapezoid equals to the sum of its two parallel bases. In this case, it is AB plus DC times the height divided by 2. The height must create 90 degrees with the base, with the bases. And again, the area of trapezoid ABCD must be equal to the sum of its two parallel bases. That is actually AB plus DC times the height, that is h, divided by 2. Again, the height h must create 90 degrees with the two bases. So in the first step, we did a construction, that is to say, from this point A, we draw perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in DC. This point is point E. And then we define the length of side DE as X, and the length of side AE as H. H is also the height of trapezoid ABCD. Why H is the height of trapezoid ABCD? Because H creates 90 degrees with the base DC. And therefore H is the height of trapezoid ABCD. In the next step, I copied the right triangle AED in the new page and we implemented the Pythagoras theorem, this right triangle AED. So actually, this is the right triangle AED that is going to the original drawing. According to the Pythagoras theorem, it is right triangle AED, AD squared, that is the square of the hypotenuse, equals to AE squared plus DE squared. Again, AD squared equals to AE squared plus DE squared. So, AD is 17. Therefore, AD squared is 17 squared, that is 289. And it is equals to AE squared. AE is 8, therefore E squared is 8 squared, plus DE squared. DE is X, therefore DE squared is X squared. So in total, actually found out that according to equation 1, 8 squared plus X squared equals to 289. In the next step, we did another construction. That is to say, from this point B, we do perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B in DC. This point is point F. We know that AB is parallel to DC. So those two angles are located between the parallel lines AB and DC, and therefore both those two angles are defined as the interior angles, and those two angles are both located in the right side of the straight line BF, and therefore they are defined as one-sided. So in total, those two angles are defined as one-sided interior angles. And according to rule 16, the sum of two one-sided interior angles is equal to 180 degrees. And therefore, the sum of those two angles must be equal to 180 degrees according to rule 16. This angle equals to 90 degrees plus the missing angle, that is angle ABF. In total, the sum of those two angles must be equal to 180 degrees according to rule 16. I repeat again, according to rule 16, 90 degrees plus the missing angle ABF, in total must be equal to 180 degrees. Here we subtracted 90 degrees from the equation and finally found out that the missing angle ABF equals to 180 degrees minus 90 degrees is 90 degrees. So actually this is the missing angle ABF, that is equals to 90 degrees in its size. Likewise, we implemented rule 16 on those two angles. Those two angles are both defined as one-sided interior angles. They are interior angles because they are located inside between the two parallel sides AB and DC, and they are one-sided angles because both of them are located in the left side of the straight line DE. So in total, they are defined as one-sided interior angles. And the sum of one-sided interior angles, according to rule 16, is equal to 180 degrees. So the sum of those two angles is equal to 180 degrees according to rule 16. So this angle is a right angle plus the missing angle BAE. In total, they must be equal to 180 degrees according to rule 16. I repeat again. According to rule 16, 90 degrees plus the missing angle BAE. In total, they must be equal to 180 degrees. Here we subtract 90 degrees from this equation and finally found out that the missing angle BAE is equal to 180 degrees minus 90 degrees is 90 degrees. So this is the missing angle BAE, that is a right angle according to rule 16. So actually found out that in quadrilateral ABFE we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this rectangle if not a square. So in relate to quadrilateral ABFE is a rectangle because it has 4 right angles. Here quadrilateral ABFE is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABFE, side AB must be equal to the opposite side FE. But AB is 16, therefore FE must be also equal to 16 units in its length. Likewise, according to the sum rule, in the same rectangle ABFE, side BF must be equal to the opposite side AE. But AE is 8, therefore BF must be also equal to 8 units in its length. What is the length of the missing line segment FC? On the drawings, it's very easy to see that FC in total equals to DC minus DE minus EF. Again, FC in total equals to DC minus DE minus EF. Repeat again, FC in total equals to DC minus DE minus EF. So FC equals to DC, that is 44, minus DE, that is X, minus EF, that is 16. So in total, FC equals to 44 minus X minus 16. 44 minus 16 is 28, so in total, this expression equals to 28 minus X, so FC equals to 28 minus X. In the next step, I copy the right triangle BFC in a new page, and we implemented the Pythagoras theorem with this right triangle BFC. So actually, this is the right triangle This is the right triangle BFC to the copy from the original drawing. According to the Pythagoras theorem, in this right triangle BFC, BC squared, that is the square of the hypotenuse, equals to BF squared plus FC squared. BC is 25, therefore BC squared is 25 squared, and it is equals to BF squared. BF is 8, therefore BF squared is 8 squared, plus FC squared. FC is 28 minus X, therefore FC squared is 28 minus X squared. So in total, according to equation 2, we actually found out that BC squared equals to BF squared plus FC squared. So BC squared equals to BC is 25, therefore BC squared is 25 squared, that is 625, and this equals to BF squared, that is 8 squared, plus FC squared, that is 28 minus X squared. So in total, according to equation 2, we should found out that 625 equals to 8 squared plus 28 minus X squared. Here we open the brackets of this expression, and finally found out that according to equation 2, 625 equals to 8 squared plus 28 minus X squared. 28 minus X squared equals to 28 squared, that is 874 plus X squared, minus 2 times 28 times X, that is minus 56X. So in total, we should found out that according to equation 2, 625 equals to 8 squared plus 784 plus X squared minus 56X. Here we subtracted 625 from this equation. After we subtracted 625, in this side of the equation we have to nothing, that is to say 0. On the other side of the equation we have 8 squared plus X squared minus 56X, and 784 minus 625 equals to 159. So in total, according to equation 2, we shall find out that 0 equals to 8 squared plus X squared minus 56X plus 159. But according to equation 1, X squared plus X squared equals to 289. So we can substitute X squared plus X squared in this equation 2 by 289. We did it, and we actually found out that according to this equation 2, 0 equals to X squared plus X squared is 289 according to equation 1, minus 56X plus 159. Here we ended 56X to this equation, and finally found out that 56X equals to 289 plus 159 equals to 448. So in total, we found out that according to this equation 2, 56X equals to 448. Here we divided this equation 2 by 56, and finally found out that X equals to 448 over 56. 448 over 56 equals to 8. So we found out that X equals to 8 units in its length. And according to equation 1, we know that X squared plus X squared equals to 289. If x equals to 8, it means that x squared equals to 8 squared, that is 64. Therefore, we can substitute x squared in this equation 1 by 64. We did it, and we should find out that according to this equation 1, x squared plus x squared, that is 64, equals to 289. Here we subtracted 64 for this equation, and finally found out that x squared equals to 289 minus 64 is 225. So in total, according to equation 1, we actually found out that x squared equals to 225. Here we took a root out of this equation, and finally found out that h equals to the square root of 25, that is 15. So actually found out that the height of this trapezoid ABCD, h, is equals to 15 units. Our mission is to find out the area of this trapezoid ABCD. The area of trapezoid ABCD equals to the sum of its two parallel bases, that is actually AB plus DC, times the height, that is h, over 2. Repeat again. The area of trapezoid ABCD equals to the sum of the two parallel bases, that is actually AB plus DC, times the height, that is h, over 2. AB is 16, DC is 44, h is 15, divided by 2. 16 plus 44 is 60, times 15 over 2. 60 over 2 is 30, so in total this expression equals to 30 times 15. 30 times 15 is 450. So we found out that the area of this trapezoid ABCD equals to 450 square units. Okay, thank you very much.